All right, so in chapter 5 here, we started talking about last time some important really sort of conversions. We had Avogadro's number, which is our 6.022 times 10 to the 23. Remember, again, these can be really atoms, they could be molecules, they really could be any unit, and that does equal 1 mole of something. And again, a reminder, when we do see the MOL, that is a mole, again, not a molecule. And really, Avogadro's number, as we talked about, is our conversion factor to go from pretty much those units. So atoms are molecules to moles and backwards. And pretty much 1 mole of anything from the periodic table will equal 6.022 times 10 to 23 atoms. Also, again, if it is a molecule, that's how many molecules will equal. Probably the most important sort of conversion factor that we do get from the periodic table is the idea of the molar mass, which is that number that you could pull from the bottom of the periodic table. And molar mass has units of grams per mole. And typically speaking, when you go about 4 significant figures, when we do pull that number off the periodic table, and that is how many grams there are in 1 mole, whatever that may be. We can also do, obviously, the molar mass for anything that's a compound as well, as you just add up all the parts basically and add them together. But molar mass is our conversion factor really to go between those 2 units, to go from grams to moles and moles back to grams. And again, that is something that we use a lot in a lot of areas of chemistry, is kind of converting things to moles. A lot of first steps that you do in things is to convert things to moles. So that's a very, very common sort of calculation that we do. Remember, again, you don't want to use Avogadro's number in every calculation, only ones that have that atoms, molecules, or something sort of involved. We also talked about calculating atomic mass, which is another sort of version of what we find on the bottom there of the periodic table. And remember, you also can kind of pull that number off as AMU per atom, AMU being an atomic mass unit. Again, not very much used a lot in our calculations in this class, again, because we do sort of measure a lot of things in grams, so we go more with the molar mass. The molar mass is numerically equal to the atomic mass in AMU, so they're sort of works out to be in the same number as you go through there. But we can't calculate the atomic mass if we wanted to. And again, you can figure out the percent abundance or relative abundance by doing some type of mass spec type of experiment like we talked about. But basically, if you wanted to calculate atomic mass, you take the percentage of the first isotope times the atomic mass of that first isotope. And then you add it to the percent relative abundance of the second isotope times the atomic mass of the second isotope. And you obviously continue that sort of pattern depending on how many naturally occurring isotopes. And that is what we also talked about, that those numbers that we do see on the bottom of the periodic table are really average atomic masses of all the naturally occurring isotopes for those particular elements, sort of calculated via a calculation sort of in this nature. Any questions on any of that there? The other thing we also talked about was you can relate these sort of calculations to a particular element. For example, in a compound, you may not be interested in the whole thing, but you can use the formula there. If you have something like CH4, you can use the actual formula as sort of a mole to mole relationship and conversion factor to allow you to go from the whole thing to just, perhaps carbon or hydrogen in this case. In this case, 1 mole of CH4 would give you 1 mole of carbon, and also 1 mole of CH4 in this case would get you 4 moles of hydrogen. And those are the numbers on the bottom, which do represent basically the subscripts there, do represent the moles of each of those ones that you have. So again, sometimes along the way there, you may have a calculation where you may be just interested in one part of it. You can use the formula as a calculation, and obviously the molar mass there to get to that mole-to-mole relationship. Any questions on any of that stuff? All right, so that's sort of where we're going to pick up here to finish out chapter 5, which is talking about really how to calculate these formulas, both the empirical formula and the molecular formula. So let's pick that up. So I think we left off here first, though, a really important part of perhaps calculating something like a molecular formula or an empirical formula, maybe more so an empirical formula, is a lot of times we can figure out the percent composition of an element in a compound. And basically, to calculate the percent composition of an element in a compound, you basically take the mass of that element. And again, if you have more than one, obviously you would multiply by the molar mass from the periodic table to do so. You divide it by the molar mass of the compound and times it by 100. And is how many moles of those that you have. And again, that would be the subscript. So if we look at something like what we got going on there on the bottom, we have C2H6O. And if we calculate the molar mass of that, I think we might even did it the other day. That's 4607 grams per mole from the periodic table. So if we wanted to calculate the percentage of carbon in ethanol here, we would find the percentage of carbon in this case would be, since there are two carbons, 2 times 12.01 grams per mole, which is the molar mass of carbon, divided by our 4607 grams per mole times 100%. And if we did that, that would get us 2 times 12.01 divided by 4607 times 100. And we'll end up with like 52.14%. We could do the same thing for the percentage of hydrogen. There are 6 of them. So we're going to take 6 times the molar mass of hydrogen from the periodic table, divided by the molar mass of the entire compound, and also times it by 100%. And if we did that, we get 6 times 1.008 divided by 4607. It's going to give us about 1313. And lastly, we obviously could do the same calculation here for oxygen. There's only 1 mole of oxygen. So that obviously would be just 16 divided by our molar mass there of the entire thing times 100%. And we got 16 divided by 4607 times 100%. About 3473. So as we can see here, by mass, this compound is mainly carbon, followed closely by oxygen, and hydrogen is the least sort of by mass element that is present in this guy. Questions on calculating percent composition. Clearly, if these are all 3 of the elements, these guys should add up to 100%. Also, when we did these 2, I could have just added the percentages and also subtracted from 100, right? And when it gave me kind of the third guy that's there. So, you could do that as well. Any questions on percent composition? Not too bad. Just basically add up the molar mass of the whole thing and then take each of the parts and divide it by the total molar mass. So percent composition is really important in terms of calculating like the empirical formula. A lot of times people figure out sort of the percent composition of elements in a compound, and it allows us to sort of figure out the empirical formula from that. So let's talk a little bit about that there. So let's first talk about the couple of formulas, and I think we have previously, but officially talk about it. There's the empirical formula, and there's really the molecular formula. And the empirical formula is the simplest whole number ratio of what is present. The molecular formula tells us exactly how much of each atom is present, or each element is present. So really, we think of empirical formulas as the simplest type of formulas. And for example, if we had a molecular formula of C6H12, that is essentially 6 carbons for every 12 hydrogens. That is the same as basically 1 carbon for every 2 hydrogens that are present. And that means that we could reduce this down in terms of the empirical formula to CH2, right? This particular case. And that's one way. If you are given, for example, a molecular formula and you're asked what is the empirical formula of it, if you can reduce it down and obviously still get whole numbers, then that would be your empirical formula. A reminder that these subscripts, as we talked about on the bottom here, are the moles, and they do need to be whole numbers. So you can't have like a half of carbon or something like that hanging out. So it's got to be a whole numbers. And with that being said, sometimes, if we had something like N2O6, in this case, that's 2 nitrogens to every 6 oxygens, if this was the molecular formula. That again is the same as 1 nitrogen for every 3 oxygens. So NO3 would be the empirical formula. So there are situations, though, where you really can't reduce a molecular formula down. So if you took something like water, water is basically 2 hydrogens for every 1 oxygen. There's no way to reduce that down and still get whole numbers. So in this case, both water, H2O is both its empirical formula and also its molecular formula. So it can be both. And in the case of water, it would be both in that particular situation. All ionic compounds are empirical formulas. So when we write ionic compounds, they are all empirical formulas. And that is because when we do put a cation and an anion together, we want to do it in the simplest way to get to 0, which means you just simplified it and you have your empirical formula. So all ionic compounds are always empirical formulas. Now, in terms of, say, something like go back this way, maybe. Speaking of this here. So let's say we had, something like H2O2, which say is the molecular formula. And that is obviously, again, here, 2 hydrogens for every 2 oxygens, which means we can reduce it down to 1 hydrogen for 1 oxygen, which means HO would be the empirical formula in this particular case. Now, if we were to calculate something like the percent composition of each of these elements in each of these formulas, we did the molar mass here of H2O2, which is hydrogen peroxide. That would be 2 times 1.008 grams per mole, plus 2 times 16 grams per mole, which would be our oxygen. So that's going to be about 34.02 grams per mole. Now, if I did the percentage of hydrogen in that, that would be 2 times 1.008 grams per mole, divided by 34.02 grams per mole times 100%. We have 2 times 1.008 divided by 34.02 times, times 100. There we go. And we'll call it about 5.926% hydrogen. And if we did our percentage of oxygen, it would be 2 times our 16 divided by our 3402 times 100%. So if we do 2 times 16 divided by 34.02 times 100, I got about 94.06%. Now, that is the percentage of hydrogen and oxygen in the molecular formula. Now, if we were to do the same calculations here for the empirical formula, let's see here. So that is going to be hydrogen at 1.008 plus an oxygen at 16. The molar mass from the periodic table of HO here would be 17.01 grams per mole. And if we calculated the percentage of hydrogen in our empirical formula, there's only one, so it'll be 1.008 grams per mole divided by 17.01 grams per mole times 100%. That gets us 5.926%. And if we did our oxygen here, 16 grams per mole for the one oxygen in our empirical formula divided by 1701, which is our molar mass of our entire thing. Going to give us for oxygen 94.06%. The percent hydrogen and oxygen in both the molecular form and the empirical form, are they different or the same? They are the same, yeah, and that's because they're just simple ratios of the same elements that are present. We have the same percentage of hydrogen in each and the same percentage of carbon or oxygen in each of these things. And again, it's because they're basically related to each other, right? They're basically the same ratio, just the simplest ratio, which means by mass, you'll have the same percentage of each of those elements that are present. Any questions on that there? Okay. So let's talk about, as we did obviously the empirical formula versus the molecular formula, let's talk about how in a more complicated way, I guess, or a more harder way maybe than just reducing down the formula to calculate the empirical formula. So in a lot of cases, you're not necessarily given the molecular formula or something like that. You'll have to calculate it. And to calculate the molecular formula, you really got to calculate sort of the empirical formula first. And it's very similar, obviously, to that experiment that we did. So let's talk about really the steps here to calculate the empirical formula. So when we're calculating an empirical formula, very often times you will be given the percent composition of everybody. So you do want to kind of convert that percent composition of all the elements into grams. And really the easiest way to sort of convert a percentage into a usable sort of number is to assume that you have 100 of it. And when you assume you have 100 grams, what that means is obviously the percentages are the same number of grams that you would have for each of those elements that are there. So a lot of times we assume 100 grams. Once you have all the elements in grams, pretty much you then want to convert it to moles. And again, that is our molar mass that we've been talking about. That is our conversion factor to do that. So you would go to the periodic table and you would do it for each element. Now, sometimes people screw up on this part with those diatomic elements like oxygen, nitrogen and stuff. So they go, okay, like oxygen is O2 by itself. So they use 32 instead of 16. But when you're doing this type of calculation, you don't know how many oxygens you have. So you should just do it based off of, say, 16, the one oxygen sort of molar mass. So remember, when you do molar mass, in this particular case, you're going to do it for just the one element by itself, even if we normally think of it as being a diatomic one, because it is not going to be by itself. It's in a formula, right? Which means it's attached to other things. So you don't have it by itself. So that's a very common mistake. Number 3 here is once you have everybody in moles, so you want to moles, you then want to divide by the smallest moles. So if we did, for example, step number 2, and we got like 2 moles of A, and 4 moles of B. In this case, we would divide everybody in this made up example by the 2 moles of A. And that would give us 1 for A, and that would give us 2 for B. And in this particular case, if we did hit all whole numbers like that, are pretty darn close to whole numbers, that would give us our empirical formula. So that would give us our empirical formula in this example, which would be AB2. Now, let's just say that we did step number 2 and we got a couple of different numbers. Let's say we did step number 2 and we ended up with 2 moles of A, but we had 5 moles of B. Here we would still divide by the smallest number of moles. That would give us 1 for A, but in this case, we would get 2.5, which would give us an empirical formula of A, B 2.5. So as we talked about, obviously these numbers here have to be whole numbers. This is too far away to round to a number, especially when you're doing book problems. In a lab experiment, maybe you would do a little bit more rounding that you normally would not do in a book problem, but in a book problem, this is too far away. So what we need to do is figure out a number that we can multiply this guy by to basically get to a whole number. So basically, if you just took 2.5 times 1, you got 2.5. If you take 2.5 times 2, you get 5, which is a whole number. And what that means, though, is, again, an error that people make is they use the 5. You're not going to use the 5. You're going to use the factor here by 2. And you do need to multiply not just that guy, but everybody by the 2. And if we did that, that would give us A2, B5, and now we have whole numbers, which would be our empirical formula. So in situations where you divide out by the smallest number of moles and you do not hit a whole number, you need to find a factor to multiply that number by and everybody by, so that you will end up with whole numbers. Very common sort of endings on numbers when you divide that are kind of too far to round, like a 0.33, maybe 0.25, maybe a 0.50, you know, those type of numbers are too far to sort of round. It really, in terms of rounding, especially usually for book type problems, needs to be very, very, very close. So like, you know, like a 0.99-ish, 0.98, you know, pretty close, or just over a whole number, like a 0.01, 02, 03, something like that. But you start getting into sort of that first decimal place that's over, a lot of times that's usually too far to round, and you kind of have to find a number to multiply it by. Again, in some cases, you may not get a perfect number every time. You may be very, very close. And if it's just a thing about a little bit of rounding in terms of when you did the calculation, then you're probably okay to round, but it usually has to be fairly, fairly close to that number. Any questions on any of those steps there? All right. All right, so let's take a look at one here together and see. So in this case here, we want to determine the empirical formula for the following percent compositions of potassium, which is 2475, manganese, which is 3477, and oxygen, which is 40.51. The first thing you want to really do when you are given the percentages here is just take a quick calculation or quick look at it and make sure you got about 100%. Again, if you do not have 100%, then you're missing some percentage for an element that's probably there. So in this case, it does add up pretty close to 100%. We're going to assume 100 grams, which is, again, basically just going to turn those percentages into grams. That means that we would have 24.75 grams of potassium. We would have 34.77 grams of Mn. And we would have 40.51 grams of oxygen in this case. The next thing that we want to do is to convert each of these into moles. So we're going to go to periodic table and convert these guys out. So potassium is 3910. There it is, 3910 grams per mole. Mn is like 54-ish, I think. 54, getting old. I can't see it. 90 something. 54. 94, we'll call it ish, depending on your periodic table and your eyesight halogen. And we'll go with 16 there grams per mole. All right, so we're going to convert all these guys into moles using the molar mass from the periodic table. 2475 divided by 3910, going to give us 0.63299 moles of potassium. 34.77 divided by 54.94, going to give us 0.63287, and 40.51 divided by 16. Give us a 2.5318 or 9 moles of oxygen. In this case, it's fairly close in terms of our smallest number of moles, but it looks like, bless you, that it is going to be Mn in this case. So we're going to divide everybody by Mn's moles, which is 0.63287, 0.63287, and 0.63287. So essentially for potassium there, we'll end up with a 1. For Mn, we will end up with a 1. And obviously here for our oxygen, we will not end up with a 1. We'll end up with a 4, basically. And in this case, we did hit pretty much all whole numbers on this. So that would be our empirical formula, KMnO4, a little potassium permanganate would be our formula in this case. Question on any of those steps there? Okay. So this is a very common way to calculate the empirical formula, percentages to grams, grams to moles, smallest number of moles, and you get your empirical formula. Now, you did a process in lab where you calculated the empirical formula as a compound, and really very simply, you could do that like you saw. You just need the mass of what you started with, right? And the mass of basically what you put on. So in the case of the first experiment, right, we put on some chlorine. In the case of the second experiment, we put on some oxygen, and knowing the masses of each of those, you could then convert them to moles, divide by the smallest, and get your empirical formula. It's a very kind of simple way. Another very common way that you could calculate the empirical formula, especially if you're dealing with some type of organic type of compound, is to actually do a combustion reaction and do combustion analysis. So let's take a look at that. So combustion analysis is pretty much a reaction that you might be familiar with, but basically you take an organic compound, and usually an organic compound will contain carbon, hydrogen, or oxygen involved. You react it with some O2, it's kind of set it on fire sometimes, and you will be able to collect CO2 and water. Will come out in a combustion reaction. So basically when you light your Bunsen burner, it's a combustion reaction. Now there is a setup where you can actually collect both of these things. So we can collect the CO2, we can collect how much water is basically coming off. And the important part of collecting both of those things is it will allow us to understand how much, in the case of CO2, how much carbon we collected. So all of the carbon in this particular reaction will come from our organic guide. So by knowing how much CO2 that we collected, we will know pretty much how much carbon was in our original compound. When we collect the water, that will tell us how much hydrogen came from our original sample, as all the hydrogen should end up in the water in this particular case. The CO2 in the water cannot be used directly to figure out how much oxygen, because what are we adding to this reaction? We're adding oxygen, which is not part of our original compound. So some of that oxygen that ends up in the CO2 And some of it that ends up in the water is obviously coming from just the oxygen that's being added in the reaction, not our originals, our compound. So that's why we're using CO2 just to find out the carbon, and the water just to find out the hydrogen, and not using them to find out the oxygen. But the good news is, if we know the starting mass of our original compound, and we use these guys to basically figure out the grams of carbon and the grams of hydrogen, we basically could take the mass of our original sample in grams and basically subtract the grams of carbon and subtract the grams of hydrogen that we collected. And what should be left at that point would be the grams of oxygen, basically. So we can use this type of analysis very effectively with organic compounds that contain carbon, oxygen, and hydrogen, as long as you know the mass of your original sample, which, you can weigh it out obviously before you begin, so you'll know how much you had to begin with. And you can figure out the mass of the CO2 and water that you collected, allow you to get the grams of carbon and hydrogen, and then you could get the grams of oxygen by difference. At this point, you will now be able to figure out the grams of each of these elements. At that point, it then just becomes a regular empirical formula type of problem. You would convert to moles, you would divide by the smallest, and you would have your empirical formula. So in a combustion analysis type of problem, you got just a little bit more of work to do up front to get to the grams of each of the elements. But once you kind of get the grams of each element, then it just kind of rolls into the normal calculation at that point. Any questions on that there? So let's take a look at one here together and see how we go through this sort of process. So here's sort of a setup. So if we were to take 11.5 grams of ethanol, which again is an organic guy that contains carbon, hydrogen, and oxygen, and we basically put it in there. Obviously, we're adding some O2. We have a water absorber and a CO2 absorber, which is obviously going to collect our CO2 and our water from this reaction. Again, the end of our combustion reaction will make CO2 plus water, so that is where it's going to be collected. So in this particular case, they collected 22.0 grams of CO2 and 13.5 grams of water. So the first thing that you would want to do is to use each of those to basically get to our grams of carbon and our grams of water. So let's go through that calculation, and it's going to kind of put together the calculation we did the other day, yesterday, to go from the whole thing to just carbon. So first off, when I look at CO2, we can use the formula like we did yesterday to figure out just the carbon part of it. And that means in 1 mole of CO2, I have 1 mole of carbon. So that's going to be an important mole-to-mole transition to get us to just the carbon. We also could look at water. And in water, for every 1 mole of water, I actually have 2 moles of hydrogen, again, from the actual formula. So much like we did yesterday, we're going to use the formula to go from the whole thing to each of the elements, which is really what we're interested in here. To do that, just like yesterday, we need the molar mass of the entire compound. So the molar mass of CO2 is going to be 12.01 plus 2 times 16, which is 32. The molar mass of CO2 is 4401 from the periodic table, if you add up everything. The molar mass of water is 2 times 1.008 plus a 16 for the oxygen, and the molar mass of water here is 18.02, which I think we also calculated yesterday at some point along the way. All right, so now we really have everything that we need. And again, that 4401 and 1802 is the molar mass from the periodic table, is where those numbers come from. We're going to do our basically grams of carbon calculation. So we're going to start with the 22 grams of CO2 that was collected. We're going to use the molar mass of CO2 to convert the whole thing into moles. So 4401 grams per mole of CO2. If I stop the calculation right now, I am in moles of CO2, but I actually just want moles of carbon. So that is where we're going to use our relationship right here. And we, again, from the equation there, we have 1 mole of CO2 will give us 1 mole of carbon in this case. So I'll get an answer here, which is 22 basically divided by 4401. Going to give us 0.4999 grams of carbon. So basically they collected 0.4999 grams of carbon from the original sample, ended up into the CO2. We will, I'm sorry, that's the moles. I know I wanted to jump way ahead there. It's kind of like grams, but not so much, I suppose. So let's try that again. That is the moles of carbon. So let me give you the right number that they collected. We will convert those moles into grams by using 12.01 grams per mole of carbon. And that would be 12.01. There we go. They collected basically 6.004 grams of carbon. So when we restate that, they collected 6.004 grams of carbon from the original sample, basically ended up in the CO2. We could do pretty much the same calculation there for our water. So starting with our water here to get us to our grams of hydrogen, they collected 13.5 grams of water. Molar mass of water, 18.02 grams per mole. Once again, if I stop right here, I'm in moles of water. I'm going to use the relationship to get the moles of hydrogen, and in 1 mole of water, there are 2 moles of hydrogen in this case. So that would get me 13.5 times 2 divided by 18.02. It's going to give us 1.4983. I'll say it right this time, moles of hydrogen. Converting our moles of hydrogen into grams of hydrogen times 1.008 gets us 1.510 grams of hydrogen. So basically in that original sample, there was 1.5 grams of hydrogen that ended up in the water. Any question on those calculations so far? So this is important because we have the grams of carbon, we have the grams of hydrogen, and we know that this sample is only made up of hydrogen, carbon, and oxygen. We do know that originally, our original sample was 11.5 grams, which is made up of the carbon, hydrogen, and oxygen. So we can now use that to figure out the grams of oxygen. And that would be our 11.5 grams minus the grams of carbon that came off, minus the grams of hydrogen that came off. And that will then tell us we should have about 3.986 grams of oxygen. Any questions on that there? So by doing this analysis, we now have the grams of carbon, we got the grams of hydrogen, we have the grams of oxygen, which is all 3 of the elements that we need. We also need the moles of each of these guys, right? So I'm going to convert my oxygen into moles, because now that we have them all in grams, we want the moles. So that's going to be 16 grams per mole of oxygen. And that means that I would have 0.2491 moles of oxygen. Now you may be wondering why maybe I got the mole calculation earlier in these calculations. That is because right now I don't now have to calculate the moles of carbon because I already wrote it. And I don't have to calculate the moles of hydrogen because I already did it. And now I have the moles of oxygen. So if you didn't get an answer there for moles and the first 2 calculations, you would need to take the grams of each of those and calculate the moles, but you actually could just back up a step in the calculation and you actually have the moles there for you. So again, if you didn't get an answer where I highlighted in the previous calculations, you would need to obviously take each of these and recalculate how many moles it would be. So since I did that, it kind of saved me a couple of calculations there to do again. At this point, I want to divide by the smallest. So let's take a look at each of these. So our moles of carbon is 0.4999. Our moles of hydrogen, 1.4982 or 3. And our moles of oxygen, which we just calculated, is 0.2491. It does look like this case, we are going to be dividing by the oxygen. So we're going to divide everybody by 0.2491, 0.2491, and 0.2491. That's going to give us for our carbon, basically A2. It's going to give us for our hydrogen, I can punch in the right number. There we go. It'll basically give us a 6. And obviously this is going to give us a 1. So we basically hit whole numbers. For example, there on the hydrogen on my calculator is like 6.01. Again, that is close enough to round, obviously, to 6. And also for my carbon, it's like 2.01 or so. If you round it, it is close enough to round. That means we all hit whole numbers. So C2H6O would be our empirical formula in this particular case. Any questions on combustion analysis? It pretty much is the same steps that you want to do before. Like before, it's just that additional sort of calculation to get to the grams. And then at that point, it pretty much is the same calculation. Any questions? So these are 2 different ways to calculate the empirical formula, which are commonly done. So let's talk a little bit about also calculating the molecular formula, which is how we go about doing that. Let's take a look here. They got the same answer again. Yeah, they did. Hey, that's good. All right. So let's talk about determining the molecular formula. So there's really kind of 3 things that you need to calculate the molecular formula. You need basically the empirical formula. So in some problems, it may be given to you. In other problems, you may have to just calculate like we've been talking about. You also need to know the approximate molar mass of the compound. The good news about that one is in book problems that is usually given to you. So somewhere in the problem, it'll usually say, hey, this compound has a molar mass of this much, or they may even give you a range in terms of the molar mass. They may say, hey, it's between like 100 and 110 grams per mole, or they may just straight up kind of give you a 1 number sort of thing, but that's usually given to you. The third thing that you need is once you have the empirical formula, either it's given to you or you calculated it, you need the molar mass of the empirical formula. And then what you do is you take the apparent molar mass of the compound, you divide it by the empirical formula's molar mass, and it will give you a number. And that number is what you would multiply the empirical formula by to get to the molecular formula. So let's just say we did this and we ended up with a 3. When we kind of divided it out. And let's just say our empirical formula was A2B4. We would multiply not one of them, but everybody by the 3, which means our molecular formula here would be A6B12 there. So that is basically what you do. Now, the one place I would say probably even in sort of book type problems where it is probably okay to round is when you do that division part right there. So if you don't get a whole number, and it can happen depending on the molar mass that's given to you, because it is an approximate molar mass, or it may be a range of a molar mass. But one place where you don't have to sort of figure out a factor, and it probably is okay to round, even if it's not perfectly right there, is probably with that calculation. Because really it should be a multiple, right? And what I mean by that is the molecular formula should be a multiple of the empirical formula, a whole number multiple as it reduces down. Any questions on that there? All right, so let's take a look at one here, and this time you do it because I'm tired. All right, so calculate the molecular formula here. The approximate molar mass of this compound is 30 grams. We have boron and hydrogen there. Boron is, I think, 1081. I think hydrogen 1.008. All right, so see what you come up with here. Okay, let's take a look here. So in this case, we have the grams of each of the elements. So really the next thing we want to do is convert them into moles. So we'll do 6.444 grams of boron. We'll go to periodic table, 10.81 grams per mole for boron. We're going to do the same thing there for our hydrogen, 1.83 grams of hydrogen divided by the molar mass of hydrogen, 1.008 grams per mole. All right, so we got a 6.444 divided by a 1081. That's going to give us a 0.59611 moles of boron. 1.803 divided by 1.008 gets us 1.7887 moles of hydrogen. In this case, obviously it looks like our boron is the smallest, so we'll divide by 0.5961 for each of these. That's going to give us a 1 there for our boron, and it'll give us, I believe, a 3 there for our hydrogen. In this case here, we did hit all whole numbers, so that is going to be our empirical formula. So our empirical formula here, which is one of the things that we need to calculate our molecular formula, is BH3. The other thing that we really need as well is the molar mass of our empirical formula. So the molar mass of this guy would be 1081 plus 3 times 1.008 for our hydrogens. Going to give us a empirical formula molar mass of about 13.83 grams per mole. So that is basically one of the 3 things that we need to calculate our molecular formula. We need the empirical formula, which we have. We need the molar mass of our empirical formula. And the last thing that we needed is the approximate molar mass of the compound, which, as I mentioned before, is typically given to you there in the problem, which would be our 30 grams in this case. So we're going to take the approximate molar mass of our compound, which is basically 30 grams per mole. We'll divide it by the empirical formula's molar mass. And that hopefully should give us a number. And in this case, we do get basically 2.169. And like I said before, this is the one place where basically it's okay to round to the nearest whole number. Again, because the molar mass that you may be given for the compound is an approximate or estimation. So it's not going to be perfect. So it may not give you a nice perfect number here. So in this case, it looks pretty close enough to 2 to call it a factor of 2. We're going to then multiply our empirical formula by 2, which means our molecular formula in this case would be B2H6. Any questions on those steps there? All right, so let's try the next one that you got going there and see what you come up with. I think we're also looking for an empirical and molecular formula on that one. So we have phosphorus, 43.64%, oxygen, 56.36. The experimentally determined molar mass is 283.89. What is both the empirical formula and molecular formula? Phosphorus, 3097. All right, let's take a look again here. We're actually given the percentages of each of these guys, and we are looking for both the empirical and molecular formula, so we do need to calculate it. Just a quick look at our percentages. We have about 100%, so that's good. Again, we're not missing anything along the way. Because of that, we could also just assume 100 grams, which will again just turn our percentages into the same numbers of grams. So we would have 43.64 grams of phosphorus. We also want to convert it into moles. So I'm here 3097 grams per mole. We also want to do obviously the same thing there for our oxygen, which would be 5636 grams of oxygen. Using the molar mass of oxygen, 16 grams per mole. Again, as I mentioned earlier, you don't want to use 32 because it's not O2 in this situation. It is oxygen with however many you have. Here we will get in terms of our moles. We got 1.4091 moles of phosphorus. We got a 5636 divided by 16 gets us 3.5225 moles of oxygen. Here we're going to divide by the smallest. In this case, it does look like it is the phosphorus. So we're going to divide everybody by the 1.4091. That's going to give us a 1 for the phosphorus. And in terms of the oxygen here, it's going to give us basically a 2.5. That means that our empirical formula at this point would be PO 2.5. And as we talked about, that is not good, right? Because you cannot have obviously a half of oxygen hanging out there. So much like we talked about earlier, we do need to figure out a number to multiply everybody by to get to a whole number. And you can probably just visualize 2.5 times 2 like we saw earlier will give us a 5. So we would want to use that as our conversion to do that. By the way, you want the simplest number to multiply to get to a whole number, not the largest. So we're going to multiply everybody here by that 2, and that will give us P2O5. And now we got whole numbers, and that should be our empirical formula in this case. Any questions on that there? So that is one of the 3 things that we need to calculate the molecular formula. We have the empirical formula. We also have the molar mass of the compound that was given to us in the problem. So the 3rd thing that we need is the molar mass of our empirical formula that we just calculated. So that's going to be 2 times 3097 plus look like 5 times 16. And that will get us 5 times 16 plus 2 times 3097. Going to give us 141.94 grams per mole. So that is our 3rd thing that we need. So we're going to take the molar mass of the compound, which was given to us, 283.89. We're going to divide it by the molar mass of our empirical formula of 141.94. And in this case here, 283.89 divided by 141.94 gets us basically a factor of 2. So that 2 is what we're going to multiply the empirical formula by to get to the molecular formula. So if you do that, that looks like a P4O10 situation happening there as our molecular formula. Any questions on any of those steps there? So while we're looking at this example, obviously the way that we're doing it is a pretty good way to do it, especially if you need to calculate the empirical formula. There is an alternative way that you could do these type of problems if you do have the percentage of each of the elements present. And since we have this example, I'll show you how to do it on this. And again, you could choose really whichever way if you do have the percentages you want to do it. But I would probably choose one way and stick with it and not kind of go back and forth. Otherwise, you'll kind of mess maybe yourself up. But I would personally recommend this way. It's a pretty straightforward way and maybe less room for error that you may have. But let's take a look at the same problem. If we sort of approached it sort of backwards, which means that if we started with the molecular formula and then wanted to get to the empirical formula, and we could do that. So from the information given to us, we actually go and get the molecular formula first, and that's what we'll do. So I'm going to erase all my scribble here, I think. All right. So if we were going to take phosphorus, I think was 3097, I said, right? And there you go. All right. So if we're going to take the molecular formula first, we do know the percentages of each of the elements that are present in the molar mass here of our molecular formula. So if we convert our percentages into a decimal, so for phosphorus, that would be 0.4364. I basically converted my percentage into a decimal divided by 100. And if I multiply that by the 283.89 grams of our molar mass, that will give me 0.4364 times 283.8. That means approximately, there's about 123.85 grams of phosphorus there in our main guy. We could then take the molar mass of phosphorus, which would be 3097 grams per mole, divided by 3097, and I hit a 3.999, which is essentially 4 there. I could do the same thing for my oxygen, take the percentage of my oxygen, which converted to a decimal, 0.5636, times it by the molar mass. And that'll basically give me how many grams of oxygen there is in our molecular formula. 0.5636 times 283.8 gets us a 159.95, we'll call it, grams of oxygen. Dividing oxygen by the molar mass of oxygen, which is 16 grams per mole. That gets us, divided by 16, approximately 9.999, which is pretty much 10 in this case. So that would be our molecular formula in this case, which was P4H, not H, O10, O10, which is hopefully the same one we got last time, I hope, yes. Now that I have the molecular formula, to get to the empirical formula, I just reduce it down, right? So I can reduce everybody to here bound by 2 and still get whole numbers. And that would get me to an empirical formula of our P2O5. So you could start with the molecular formula and work your way backwards if you have the percent composition by mass of each element, and then just reduce down your molecular formula to get to your empirical formula. And that's another alternative approach to it. Personally, if you, I would probably go the other way. Again, a little bit less room for error. A lot of people always mess this one up trying to remember, what am I supposed to multiply by or divide by? So I'd probably go the other approach, but this is, a good approach as well. Especially you go the other approach if you don't have the percentages, because you're just wasting time calculating the percentages to go back, so you might as well just roll the other way in most of the cases. Any questions on an alternative sort of approach there? All right, let's take a look at one last one then. A little vitamin C, carbon 12.01, hydrogen 1.008, and oxygen 16. All right, empirical molecular formula of vitamin C has an approximate molar mass of 176.13. So again, I'm gonna go kind of the first approach we've been talking about. I got basically 100% when we add those together. I do have the approximate molar mass of the compound given to us. So we do need to calculate our empirical formula. So I'm just going to assume 100 grams and take that approach. And that means I got 40.9 grams of carbon. We're going to divide carbon by the molar mass of it, grams per mole. We're going to take 4.58 grams of hydrogen, divide by the molar mass of hydrogen. And lastly here, we're going to take 54.5 grams of oxygen, divided by the molar mass of oxygen. And that's going to get us here 40.9 divided by 12.01. We got 3.405 moles of carbon, 4.58 divided by 1.008, 4.544 moles of hydrogen, and 54.5 divided by 16, 3.406 moles of oxygen. In this case, they're pretty close. We'll go by either of the 3.4s, looks like is what we should divide by. So we'll divide everybody here by 3.405, 3.405, and 3.405, basically 1.33, I believe, in that case. So in this case, we end up with an empirical formula of C H 1.33 and O. Once again, that is going to be a little bit of a problem for us as it's not a whole number. So we do need to figure out that factor. So if we just run through the list there, starting with 1.33 times 1, 1.33, 1.33 times 2, 2.66, getting closer, 1.33 times 3. That is 3.99. That is pretty much close enough to 4 to call it 4. And that means that we will multiply our everybody by this factor of 3. That gives us C3H4O3, and that should be our empirical formula. Any questions up to there? So that is the second thing that we need to figure out the molecular formula. We still now need the empirical formula's molar mass. So we got 3 times 12.01 for our carbons, plus 4 times 1.008 for our hydrogens, plus 3 times 16 for our oxygen. So that's going to be a 3 times 12.01 plus a 4 times 1.008 plus a 3 times 16. Going to give us a 8806 grams per mole. So using our empirical formula as molar mass and the one given to us in the problem there, just scribbled all over 1676.13 divided by 8806. Going to give us a factor to multiply that by of I'm believing 2. So we're going to take our empirical formula and multiply it by 2, C6, I hope, H8O12, I hope. That's like 12. I know it's getting the eraser. It's all right. All right, I'm holding a calculator. All right, so that's 3 times 2. I'm gonna use my fingers there. I think you said 6 there. That sounds better, probably. There you go. Any questions on that? You obviously in this problem could have done the molecular formula first and went backwards. Again, in that situation, if you want to do it that approach, you would basically take 0.409 times the 176.13 divided by 1201, and then do the same thing for the others, and then you should end up with C6H8O6, and then you can reduce it down. Everybody there looks like by 2 would get you back to your empirical formula. Any questions on calculating molecular formulas, empirical formulas, any of those things? All right, so that wraps up chapter 5.